Welcome to Tomorrow Unveiled, the deep dive designed to get you thoroughly informed on the defining technological collisions of our time. Today, we are grappling with, what has to be the biggest power struggle in modern tech. It's this explosive, surging demand from artificial intelligence colliding head-on with some truly revolutionary supply technology.
It really is the energy story of the decade, and our title for this deep dive, I think, captures it perfectly. Green code, hot core.
Right.
The green code side, that represents the resource-intensive, soaring world of AI, the algorithms, the data centers, all of it. And then the hot core, well, that represents the necessary, reliable, high-density power breakthroughs. We're talking next-generation geothermal and advanced nuclear that are really rising to meet that challenge.
And that collision is exactly what we are here to unpack for you. Our mission really is to cut through all the abstract hype around AI. We want to understand its true, measurable environmental cost, and then, crucially, figure out what firm 247 power sources are actually capable of matching this completely unprecedented demand.
And our dedicated research team has compiled a huge stack of materials on this. Everything from the unseen water footprint of large language models to the radical acceleration we're seeing in fusion and advanced geothermal drilling.
Okay, so let's just start with a shock factor. If you need one data point to really frame this, where do we start?
Well, if you're looking for that single data point to encapsulate the scale of the problem, let's start right here. For years, the public conversation focused so narrowly on the massive one-time energy cost to train a large AI model.
Right, that's the number that makes the headline.
Exactly. It makes headlines, but then it fades quickly. But the data compiled by the research team highlights this really alarming estimate. One single year of using a service like ChatGPT, so we're talking about inference, can generate 25 times the carbon emissions of that model's initial training process.
Wow. Okay, wait. 25 times. Not 25% more. 25 times the training cost.
25 times. Just from the accumulated daily use of billions and billions of queries.
When you look at it that way, it completely reframes the entire energy calculation. We're not talking about a capital expense anymore. This is an operational expense that is exponential, compounding, and continuous. It's a persistent, massive energy drain that we have barely even begun to track.
It forces us to redefine the problem. We have to move beyond those flawed narratives. So throughout this deep dive for Tomorrow Unveiled, we're going to meticulously unpack these hidden liabilities of AI, its energy hunger, its massive water consumption, its material waste footprint. Then we'll pivot to the solutions. We'll explore the global geothermal renaissance, the state of advanced fission and fusion, and finally, the essential policy and software strategies, the green code, accountability you could call it, that's designed to govern this entirely new energy reality.
Okay, let's jump right in with the demand side then. And that means confronting what the research team calls the inference iceberg. It's a great analogy because for so long, all the discussions around AI's environmental impact focused only on the tip of that iceberg. The sheer computational brute force required for training, that was the easy, visible target.
And that focus gave a completely misleading picture of the long-term impact. It really did. Training is a finite, one-time investment. You could think of it like building a massive manufacturing plant. The inference phase, though, that's the daily cumulative use. Every query you type, every auto-generated image, every piece of code it writes for a developer, that's the persistent, ongoing running cost of that factory. It's the long tail of consumption that really defines the industry's environmental profile.
And the numbers that our team compiled are, well, they're simply undeniable. The consensus is that inference is the dominant long-term cost, potentially accounting for, an astonishing 60% to 90% of a model's total lifecycle energy consumption?
That's right, 60 to 90%. We were talking about a persistent, massive energy drain that just accelerates and accelerates as these models become more embedded in our daily lives, in consumer and enterprise applications.
And this inherent computational hunger, it immediately raises this core philosophical conflict in AI development today. It's this battle between what our sources call red AI and green AI.
Yeah, and red AI is the philosophy of brute force. It's just relying on massive amounts of computational power and huge generalized models with hundreds of billions of parameters, all because they yield maybe slightly better results than smaller alternatives. It's a more is more approach.
So if red AI is bigger is better, what does green AI offer as the alternative?
Green AI, by contrast, is all about efficiency, size, and sustainability. It aims for models that can achieve really high performance, but with just a fraction of the computational load. And the research our team put together points out this isn't just a theoretical difference. It has profound practical implications.
Can you give us a concrete example of that contrast in efficiency? What does that actually look like?
Absolutely. One of the most effective green AI strategies is, honestly, just selecting the right tool for the job. It's that simple. You don't need the computational density of a massive multi-billion parameter model to do a simple coding task or, say, summarize a short text.
It's like using a sledgehammer to crack a walnut.
That's the perfect analogy. It works, but it's grossly inefficient. Choosing a smaller, specialized model that's been optimized for that specific function that can reduce the energy use for that task by up to 90%. Green AI finds the nutcracker.
And when you scale that inefficiency up across billions of daily queries, you start to see why the energy footprint is so astronomical. The research team's data on a model like GPT-3, for instance, the initial training cost was estimated at 1,290,000 kilowatt hours.
An enormous number. But a specialized, high-performing green learning model for a specific equivalent task might only need about 32.4 kilowatt hours.
The disparity is just staggering. It feels like it should fundamentally change how companies, universities, even governments approach AI procurement. You're not just buying software. You're subscribing to a massive, ongoing energy liability, unless efficiency is really prioritized from the start.
Precisely. And that massive energy demand, that incredible computational load, is inseparable from intense heat generation. And intense heat demands massive cooling systems, which introduces the next major liability we have to talk about, the hidden water footprint.
This is truly a dual crisis, and one that is becoming, I think, a lot more visible in recent years. The high-performance GPUs and TPUs powering these AI models generate heat so intense that data centers have to rely on these huge evaporative cooling systems, and they are just voracious consumers of fresh water. We need to distinguish clearly between what the sources call Scope 1 and Scope 2 water use to really grasp the full cost here.
Understanding that distinction is absolutely vital. So, Scope 1, or direct use, is the on-site fresh water. It's withdrawn from local sources, rivers, reservoirs, municipal supplies, and it's directly consumed by the data center's cooling towers.
And when it evaporates to cool the machines, it's just gone from the local watershed, right?
It is permanently removed from the local watershed. That's the visible, measurable use that people think of.
But the research shows that Scope 1 is, and this was surprising to me, the smaller fraction of the problem.
It is, which is often counterintuitive to the public. The overwhelming majority is Scope 2, or indirect use. This is the much, much larger amount of water used off-site by the power plants, whether they are gas, coal, or nuclear, to generate the vast quantities of electricity the data center consumes.
So hold on. For most U.S. data centers, the research estimates this indirect water use accounts for, what, 80% or more of the total water footprint?
That's the number, 80% or more.
So let me get this straight. If I type a simple query into a generative model, and the total water consumed for that query is, let's say, 500 milliliters. A small bottle of water, 4/5 of that isn't from the data center's cooling towers, but from the power plant that supplied the electricity for that one query.
That's exactly the right way to think about it, and the research breaks it down. A single GPT-3 query might consume about 16.9 milliliters of water, but nearly 87% of that is the hidden Scope 2 cost of electricity generation. So the water cost is primarily dictated by the carbon intensity and the type of the local power grid, not just the physical cooling system on site.
And the cumulative scale of this consumption is just staggering. The research team synthesized estimates showing that training a single large model like GPT-3, it consumed an estimated 700,000 liters of clean fresh water.
That's over 185,000 gallons. It's hard to visualize.
Yeah.
That is a literal tanker truck of water, just for a one-time process.
And this scale is now showing up in corporate reporting, isn't it? This isn't theoretical anymore.
Not at all. One major tech company whose AI operations have ramped up dramatically reported a 34% increase in their total water consumption from 2021 to 2022. Another showed a 20% increase in that same period. This is a massive, sudden surge in industrial water demand that is happening in very specific geographical areas.
And that leads directly to the environmental justice aspect the research team highlights. If this consumption is so concentrated, what does that mean for the communities living there?
This is a crucial point that goes beyond simple consumption numbers. Data centers need reliable power, but they're often strategically built in hot, arid regions because, land and certain cooling systems can be cheaper there. The critical finding from the research is that an estimated 2/3 of new U.S. data centers are located in high water stress areas.
What does high water stress area mean practically for the residents? Are we talking about aquifers running dry, conflicts with local agriculture?
Exactly that. We are talking about regions where the natural recharge rate of aquifers and reservoirs just cannot keep pace with the demand. So when a massive data center moves in, needing millions of gallons of water annually just for evaporation, it pits the tech industry directly against local communities, agricultural needs, and indigenous nations for an increasingly diminishing resource.
Yeah.
It accelerates depletion, it lowers water tables for residents, and it can force severe quotas on farming.
And this creates a really complicated trade-off dilemma for the operators, right? Because if they try to be responsible and reduce their Scope 1 direct water use by switching from evaporative cooling to, say, air cooling systems, they immediately increase their electricity demand, potentially by 10% or more.
Which then increases the much larger hidden Scope 2 water footprint from the power plants. It's a vicious circle. Operators in these water-stressed regions are forced to navigate a zero-sum trade-off. It's global climate goals versus local water needs. There is no simple, consequence-free decision under the current infrastructure model, which is why a shift to reliable, low-water intensity power generation, these hot core solutions, becomes so vital.
Okay, let's widen the lens beyond energy and water now and look at the physical costs involved. Let's move to the systemic footprint. We're talking about the hardware itself and this concept of a full life cycle assessment, or LCA.
An LCA forces us to look past the monthly energy bill and look at the embodied costs hidden in the hardware. Generative AI is driving this exponential demand for specialized high-performance GPUs and TPUs. And these things are incredibly complex to manufacture and, critically, have a very short operational shelf life. The hardware lifecycle is accelerating, making these components quickly obsolete.
Which creates a huge specialized e-waste problem.
A huge one. And manufacturing those specialized chips requires significant raw material extraction. Cobalt, lithium, rare earth metals, often sourced through ecologically damaging mining procedures overseas.
So what does the full LCA show?
Well, one assessment of a generative AI service found that the end-user terminals and networks, so we're talking about our laptops, our phones, the infrastructure connecting us, accounted for a massive 85% of the abiotic depletion potential.
Abiotic depletion potential. That sounds like serious jargon. Can you simplify that for us?
Yeah, it's a mouthful. It's essentially the measure of raw material extraction and consumption. It tracks how fast we are using up non-living resources like metals and minerals. The fact that our devices account for 85% of that depletion means the environmental cost is literally in your hand, driven by the need to continuously upgrade your hardware just to keep pace with these new AI demands.
This brings us to a fundamental economic reality that just sabotages any efficiency gains we make. Jevons paradox, or the rebound effect. It's funny how a 19th century idea perfectly describes our 21st century AI problem.
Jevons paradox is counterintuitive, but it's pretty much unavoidable in technology. It argues that as a technology becomes more efficient, let's say a new, faster GPU cuts the cost of running a query, the demand for that service explodes exponentially,
So efficiency leads to lower costs.
which encourages far greater adoption, leading to a net increase in total resource consumption. We get dramatically more efficient at using the resource per unit, but we end up using so many more units of the technology that the overall environmental problem just scales up anyway.
So if we make AI 10 times more efficient, the resulting lower costs could cause demand to jump 20 times, and we're actually worse off environmentally. That's a fundamentally insidious threat to sustainable development.
It is, because it means simply improving hardware efficiency isn't enough. We need profound shifts in how we manage demand and governance. And this brings us to what the research team identified as the non-green code risk.
This is fascinating and, frankly, pretty concerning. It suggests the environmental problem is being baked directly into the software itself by the AI tools we're using to write that software.
That's exactly it. Developers increasingly rely on GenAI tools to write or auto-complete their code. However, investigations reveal that these tools often exhibit a default non-green behavior. When asked to perform simple file reading or input-output tasks, they consistently default to energy-inefficient I/O functions instead of more sustainable, optimized alternatives.
So AI is literally writing code that is inherently power-hungry.
Precisely. It is scaling the environmental problem at the foundational software level, effectively accelerating the red AI philosophy, regardless of what the developer intended. We're embedding energy hunger into the very infrastructure of the digital world simply because the GenAI tools were trained on and therefore default to these computationally expensive methods.
But all of these measured costs, The energy, the water, the e-waste, they all rely on information that's incredibly hard to get. And that brings us to the final and maybe the most critical barrier, the corporate black box of accountability.
The lack of transparency regarding the true energy consumption, water usage, and carbon footprints of these proprietary large language models is the single greatest obstacle to any kind of governance and accountability. Companies treat this environmental data as proprietary trade secrets. They cite competitive advantages.
So if the environmental cost is a trade secret, how can we possibly fix it or even measure it accurately?
We can't. Not really. This opacity forces researchers to use bottom-up estimates, which are almost universally acknowledged as a lower bound. They can't access critical real-world data, especially regarding cooling, which we now know is a major energy and water consumer. The research team emphasized this point with a powerful analogy. Trying to measure the environmental cost of AI without transparency is like trying to calculate the calories in a food product without access to the nutrition facts label. The information is intentionally withheld.
And when environmental data is intentionally withheld, responsible policymaking becomes basically impossible. Governments and regulators can't effectively manage an industry whose true impact they are legally prevented from measuring.
And this lack of full cost accounting prevents institutions, whether they're massive corporate buyers or government agencies, from making sustainable procurement decisions. They're asked to choose a vendor without knowing the environmental cost per transaction, so they risk selecting the most computationally expensive option simply because it's the biggest name. The consensus is clear. We have to demand transparency before procurement.
This entire section paints a picture of massive, escalating, continuous demand. The sheer scale of the energy required for AI compute is forcing the entire power sector to look for solutions that are equally massive, reliable, and available 24/7. And this brings us directly to the supply side, to the hot core.
That intense demand from AI, that need for massive, reliable 24/7 baseload power, is the primary driver for the explosive renaissance we are seeing in deep thermal energy. Geothermal is moving from a niche technology, confined to naturally hot spots like volcanic regions, into a globally scalable baseload source.
What evidence do we have that this isn't just industry hype, but a real, measurable market shift?
The evidence is compiled comprehensively in the 2025 U.S. Geothermal Market Report. And the numbers are really compelling. Just look at the rate of change. Installed capacity in the U.S. increased by 8% in the last 4 years, between 2021 and 2024.
Okay, 8%.
Now, compare that acceleration to the prior 4-year period, where capacity only increased by 1%. This is a 7-fold acceleration in deployment speed.
Wow, that kind of growth demands capital. How much private investment is pouring into this space?
Since 2021, over $1.5 billion in private capital has been invested specifically in these next-generation geothermal companies. But maybe the most telling metrics are the contracts being signed, because contracts reflect actual commitment. The report shows 26 new power purchase agreements, or PPAs, were signed in that short window. That's more than double the number signed in the entire 5-year period before it.
And this is where we close the loop back to AI. Are these contracts for just general grid supply, or is there a direct link to the new digital demand?
There is a very direct link. What we found is that several of these new PPAs are specifically for power supply to AI-driven data centers. And the reason is simple. Data centers need 2 things: scale and reliability. Geothermal delivers high capacity factors, we're talking 90% or higher, which intermittent renewables like wind and solar just can't guarantee on their own. For an AI firm running multi-billion-dollar compute clusters, a guaranteed 2047 firm, clean power source is worth paying a premium for.
So how is this dramatic shift from niche to globally scalable actually technologically possible? This brings us to the Enhanced Geothermal Systems, or EGS, breakthrough.
EGS is the revolutionary concept that changes the resource map entirely. Historically, geothermal required 3 things to line up perfectly: high heat, underground water, and permeable rock. EGS removes the last 2 requirements. It's an engineered solution. We inject fluid, usually just water, into deep, hot, dry underground rock to create an artificial controlled heat source reservoir. This fundamentally unlocks geothermal potential anywhere the heat is deep enough, which is virtually everywhere on the planet.
Now, this is where I have to play the skeptic for our listeners. The research notes that this success is driven by repurposing technology honed in the unconventional oil and gas industry, specifically horizontal drilling and hydraulic fracturing. If we're borrowing fracking tech, doesn't that immediately raise major environmental concerns, like induce seismicity or aquifer contamination, even if it's just water being injected?
That is an absolutely necessary and critical question to ask, especially given the history of the techniques being borrowed, and the industry is highly aware of the public perception. The key difference in EGS deployment versus typical hydrocarbon extraction fracking lies in the materials and the depth. EGS primarily uses plain water, not the complex chemical cocktails often used in oil and gas fracking. And crucially, the engineered reservoirs are often drilled much deeper than typical fracking operations, way past the basements of freshwater aquifers into what they call basement rock.
So the goal is to target and control the fracture area, but with a less volatile medium and deeper down where it can't affect drinking water.
Yes. The industry's regulatory framework and the R&D at test sites are heavily focused on mitigating induced seismicity, which is a real risk, no doubt.
Yeah.
But by carefully controlling injection pressure and monitoring the fracture networks in real time again, often using green code-style dynamic software, they aim to manage that risk, making EGS a much cleaner process than its oil and gas predecessors.
The research points to the critical role in de-risking this technology belonging to the Department of Energy's Utah Forge site. This is a field lab specifically designed to test and prove these new drilling and engineering methods under real-world conditions.
Utah Forge is absolutely essential because the primary inhibitor to commercial EGS has always been cost, and cost is largely determined by drilling time. Drilling through deep, hard granite is incredibly expensive. The research documents a major, almost unthinkable efficiency gain at the site. The time required for drilling was substantially lowered from 310 hours in 2020 to just 110 hours in 2023.
That's a 65% reduction in drilling time in just 3 years. What does that efficiency gain translate to in the real world for a developer?
It translates directly into commercial viability. If you can move from months to just days of drilling, you shave millions off the capital expenditure for every single well. That rapid cost reduction is what makes EGS ready for large-scale adoption. We're already seeing a 400-megawatt project underway near the site. This is the difference between an interesting science project and a globally scalable baseload power source.
So we have a technology that provides 247 baseload power, it's globally scalable, and its costs are rapidly declining. But the business case is getting even stronger thanks to new revenue streams that diversify the project risk.
That's right. Diversification is becoming a standard feature of these next-generation geothermal projects. They're starting to integrate the process of direct lithium extraction from geothermal brines.
So they're generating power and at the same time producing critical minerals for the battery supply chain from the same operation.
Exactly. The geothermal brine, that's the hot water circulating deep underground, is naturally rich in lithium. Using integrated, closed-loop extraction processes, they can pull out the lithium before the water is re-injected back into the earth to continue the geothermal power cycle. This creates a dual revenue stream power plus critical minerals. It makes the geothermal project economics significantly more attractive to private investors, and it supports the broader energy transition. It's turning what might have been a waste product into a valuable asset.
It's a beautifully efficient system, ensuring that the same infrastructure that provides the firm, clean power for the digital world also provides the critical materials for electric vehicles and grid battery storage.
If geothermal is the quiet, commercializing renaissance, then advanced nuclear, both fusion and fission, is the high-stakes, high-octane technological race to supply the ultimate dense, reliable power source.
Let's start with the ultimate hot core goal, fusion. Historically, fusion research was just dominated by these slow, massive government projects that were measured in decades. But the sources highlight a complete paradigm shift. It's now modular, private sector-driven, and, crucially, it's leveraging AI digital control systems.
The convergence of green code efficiency and hot core physics is nowhere clearer than in fusion. You could just consider the high-profile partnership between Commonwealth Fusion Systems, CFS, NVIDIA, and Siemens. They're collaborating to create a high-fidelity digital twin of the physical spark fusion machine.
A digital twin is more than just a simulation, isn't it? It's a real-time, AI-powered virtual replica. How does that accelerate something as complex as plasma physics?
Fusion plasmas are notoriously difficult to control. They're volatile, hot, and highly unstable. The physical spark reactor just saw the installation of its first magnet at CES 2026. This is the first of 18 high-temperature superconducting magnets designed to contain plasma hotter than the center of the sun. The digital twin running on these advanced platforms allows engineers to integrate real-time experimental data, tens of thousands of sensor readings every second, with high-fidelity AI physics models.
So the AI is not just predicting what will happen, it's actively learning the system's behavior and potentially providing dynamic control inputs faster than a human operator ever could.
Precisely. This dramatically accelerates the learning curve. It reduces the immense capital risk involved in physical experimentation, and it's necessary for creating the dynamic controls needed to maintain stable plasma, which is required for sustained energy gain. You learn the operational parameters of the reactor digitally before you risk the multi-billion-dollar physical machine.
That focus on rapid, iterative engineering is a major theme across the entire fusion landscape. We're seeing breakthroughs happening at a pace no one expected 5 years ago.
Just look at the global milestones gathered by our research team. In Israel, the compact fusion company NT Tau achieved first plasma in their C3 prototype in just over 2 months from the start of assembly.
2 months? That's an unheard of timeline.
It is. That 2-month timescale is a strategic statement. The goal is to compress that simulation to validation pipeline to less than a year, allowing for continuous, rapid technological cycles, a massive departure from the decades-long approach of previous generations.
And on the fundamental physics side, we have China's experimental advanced superconducting tokamak, or EAST, which recently pushed boundaries on plasma density.
That's a highly significant achievement for commercial viability. They accessed what's called a density-free regime. This matters because thermonuclear power output scales with the square of the fuel density. So proving that plasma can remain stable at densities well beyond conventional limits, well, it suggests a practical pathway for increasing the power output of future reactors without having to increase their massive physical size. This is essential if fusion is to ever be compact and commercially deployable.
Finally, we need to mention Thea Energy's stellarator design, Helios, which received preconceptual certification from the U.S. Department of Energy. Stellarators are typically seen as being even more geometrically complex than tokamaks, but Thea's design seems to simplify the engineering challenge.
It does. Their approach uses a planar coil architecture, which simplifies manufacturing and maintenance significantly compared to the twisted, complex magnet coils of traditional stellarators. Crucially, they use dynamic software controls on their magnet array. The system is intentionally designed to tolerate minor manufacturing imperfections and gradual wear and tear through dynamic green code adjustments, rather than relying on rigid, costly physical tolerances. This focus on practicality and reliability aims for an impressive 88% capacity factor through an achievable biennial maintenance cycle.
So fusion is getting faster, smaller, and smarter through digital control. But while fusion remains a 2030s prospect, advanced fission is commercially ready right now. Let's shift to the immediate answer for AI demand: small modular reactors, or SMRs.
SMRs are the most commercially mature segment of advanced nuclear technology, and they are designed perfectly to address the AI demand problem. They're advanced fission reactors, typically generating under 300 MeV, and they're engineered for factory fabrication.
That modular approach is the key differentiator, isn't it? It just changes the economic risk profile entirely.
It does. Traditional nuclear require these immense multi-billion-dollar one-off construction projects on site that often took 10 or 15 years and were prone to massive cost overruns. SMRs, by contrast, are manufactured in a controlled environment and then rapidly deployed on site, usually in 12 to 24 months. This standardized, modular manufacturing process dramatically reduces the capital risk and accelerates deployment speed.
And big tech isn't waiting for a theoretical future grid. Our sources show they're aggressively adopting nuclear now to meet that massive, escalating AI demand.
The demand is translating directly into massive contracts. It shows these companies view reliable, emissions-free power as a core competitive necessity. The research team notes Amazon's acquisition of a nuclear-powered data center, Meta's 20-year deal for emissions-free nuclear energy, and Google's commitment to buying power from future SMRs. This demonstrates a strategic recognition that only reliable 24/47 clean power can guarantee the energy security and massive capacity required for multi-site AI compute needs.
They aren't just buying clean power, they're buying grid stability and capacity density.
Exactly. And the industry is finding ways to deploy this quickly and cost-effectively, particularly through infrastructure synergy transforming decommissioned coal plants into new nuclear sites.
That synergy must save a fortune and accelerate the timeline significantly.
It's a winning strategy on multiple fronts. By reusing these sites, you utilize the existing land, the critical water access required for cooling, and, most importantly, the high-capacity transmission lines already connecting that site directly to the grid. The Department of Energy estimates that transforming these brownfield sites can save up to 35% on construction costs, accelerating SMR deployment while simultaneously revitalizing communities that previously relied on fossil fuel generation. This is how the hot core strategy serves as a pillar for both clean power and economic transition.
The scale of this new energy future geothermal fission and fusion, it's immense, and it requires us to pause and reflect on the rapid convergence of these technologies.
It is a moment of necessary transformation. If you're listening to Tomorrow Unveiled on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could take a moment to leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
And if you're finding this insightful on YouTube, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. Now that we've established that the technology, the hot core, is moving fast, we have to talk about the governing framework. Technology alone won't solve the climate crisis unless the rules, the green code, catch up. And that framework has to address the bottlenecks that slow down the build-out of this critical infrastructure, which brings us to permitting reform.
The single greatest bottleneck for clean energy infrastructure, particularly high-density, high-capital projects like enhanced geothermal systems and SMRs, has been the decades-long federal permitting process, specifically under the National Environmental Policy Act, or NEPA, and the challenges of getting transmission lines approved.
The major legislative response noted by our research team is the recently passed SPEED Act in the House, which aims to modernize NEPA. These reforms sound like they are strictly for speed and predictability, which the industry desperately needs. But what are the key provisions that actually bring certainty to these projects?
The SPEED Act proposes sweeping reforms designed to address the litigation and ambiguity that plagues development. First, it establishes strict judicial limits. This sets a short, critical 150-day statute of limitations for filing NEPA claims once a project is approved.
That is huge. So if you're an environmental group or a local opponent, you have to launch your challenge quickly, or you lose your chance. But doesn't a 150-day window, couldn't critics argue this just guts meaningful environmental review? Is this simply fast-tracking environmental damage?
That is the central political conflict around the act. Industry proponents argue that it doesn't reduce the rigor of the review itself, but rather targets abusive, prolonged litigation that's used simply to stall projects years after all the necessary studies have been completed. They contend that by providing predictability, it enables capital to flow into projects like SMRs, which require immense upfront investment based on reliable deployment schedules. The goal is to enforce the timeline, not reduce the environmental standards.
I see. So certainty is key. What's the second major provision addressing that certainty?
Second, the Act enforces project certainty by prohibiting federal agencies from rescinding or rendering ineffective previously completed environmental documents. This is a direct response to the whiplash effect, where a change in presidential administrations or regulatory priorities causes a completed permit to be reversed, forcing developers to restart multi-year studies. For projects with decade-long timelines, this predictability across political cycles is indispensable.
And the third provision directly addresses the scope of the environmental review itself. Traditionally, NEPA reviews often balloon because agencies are asked to evaluate incredibly speculative upstream or downstream consequences of a project.
The Act directly restricts reviews to effects that are proximately caused by the project itself. This is a critical legal limitation that focuses the environmental assessment solely on the direct impacts of the facility under consideration. It avoids endless legal disputes over highly speculative or remote effects far removed from the project site.
So no more arguing about the global impact of the copper mine supplying the components for the factory that's supplying the transmission lines. It focuses the review on the physical plant itself.
Exactly. This is the governing framework trying to catch up to the reality of large-scale infrastructure deployment. For hot core technologies, where billions are invested based on deployment schedules, this predictability is vital to move these multi-decade projects from the drawing board into the operational grid.
But the policy conversation can't just be about speed. It must also be about accountability. This returns us forcefully to the AI black box and the need for mandated transparency.
The lack of transparency we discussed earlier is the greatest barrier to governing the digital footprint. If the industry is scaling exponentially, and we cannot manage what we cannot measure, the inevitable result is runaway environmental costs. The consensus among the research community is that a full cost accounting must become mandatory before procurement.
So the research team proposes a strict set of conditions for vendors seeking government or institutional contracts, using the power of the buyer to force transparency. What specifically must these companies report to get a contract?
They need to disclose 3 key verifiable metrics at a minimum. First, energy consumption per 1,000 queries, which quantifies the operational inference cost. This must be a standardized metric allowing for a direct apples-to-apples comparison between models. Second, total water footprint, strictly separating the direct Scope 1 use from the much larger indirect Scope 2 use. This reveals the true local impact versus the systemic impact.
And the third metric addresses the problem of companies claiming to be green just because they bought carbon offsets, even if they're using the dirtiest grid on the planet.
That's right. The third requirement is the disclosure of data center locations and the specific carbon intensity of their power grids. Knowing where the computation is happening reveals whether the company is truly committed to clean power procurement or simply masking the use of dirty grids behind carbon credits and vague clean energy claims. This is essential for preventing greenwashing at scale.
That is the external enforcement of the green code. Let's pivot to the internal, the software strategies developers can actually use today to reduce that massive AI footprint.
This is about shifting the entire institutional mindset from the bigger is better, that red AI approach, to smarter is better, or green AI. The goal is to maximize efficiency at the algorithmic level, essentially rewriting the code for sustainability.
What are the main optimization techniques that fall under this green AI umbrella?
There are 3 core techniques detailed in the research. The first is knowledge distillation. This is where you take a massive energy-hungry teacher model, a billion-parameter behemoth, and you create a much smaller, highly efficient student model that mimics the performance of the teacher, but with fewer computational resources.
Can you give us a real-world impact example of that distillation? How much of a difference does it make?
The famous example is DistillBERT, which is 40% smaller and 60% faster than the original BERT model, while retaining 97% of its performance accuracy. That translates directly into vastly reduced server space, lower power consumption, and quicker response times for the end user. High performance with vastly lower energy demand.
And the second 2 techniques are related to model optimization, making the models themselves leaner.
They are. Model pruning involves trimming away useless, redundant connections or parameters within a neural network to make it smaller and faster without significant performance loss. Then there is quantization, which simplifies the model's math. Instead of using 32-bit floating point numbers for calculations, which requires more processing power, it simplifies to 16-bit or even 8-bit integers.
It's basically optimizing the arithmetic, saving memory and energy at the foundational processing level.
Exactly. Every bit of memory you save is a bit of energy you don't use. And the final technique avoids massive training costs altogether.
That's transfer learning.
Transfer learning is arguably the most efficient green AI strategy. Instead of paying the massive computational cost of training a model from scratch, that 1.3 million kilowatt-hour cost we discussed, you recycle a large pre-trained model and simply fine-tune it for a new similar task. This completely sidesteps the massive upfront energy cost and significantly reduces the total lifecycle environmental liability.
Beyond the algorithms, there's also the infrastructure optimization strategy that leverages the difference in grid cleanliness we discussed earlier. Geographical load balancing.
This is a powerful, practical, and highly dynamic strategy. Instead of running a computational task in the nearest data center, which might be on a dirty grid one heavily reliant on natural gas or coal, geographical load balancing involves intentionally shifting training and inference workloads to data centers located in regions with low-carbon grids.
So you're routing the query to Sweden or the UK, where there is high renewable output, rather than to a local data center in a coal-heavy region.
Precisely. The research cites examples of companies intentionally moving workloads to places with high wind or hydro availability to dramatically reduce the carbon footprint of the exact same computational task. This is the ultimate green code, move matching the variable demand of AI compute to the variable low-carbon supply of the hot core grid. It's a smart way to match efficiency with infrastructure availability, saving on the carbon cost, even if the computational cost remains the same.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the convergence of AI demand and next-generation power, or if you have experience with green AI or the SMR transition.
To synthesize this convergence, the explosive and often hidden demand from AI, characterized by that massive 25x inference cost, is forcing an immediate, systemic shift to high-density, reliable, hot-core solutions. This includes advanced nuclear energy, both advanced fission like SMRs adopted aggressively by big tech, and the rapid fusion development leveraging digital twin technology. And crucially, it also includes the geothermal renaissance, where enhanced geothermal systems, accelerated by efficient drilling technology and de-risked at sites like Utah Forge, are proving geothermal to be a globally scalable 247 power source.
And this technological leap is simultaneously pushing the urgent need for policy and software accountability. We're seeing real regulatory actions, such as the SPEED Act streamlining permitting and providing project certainty for these multi-billion-dollar ventures. Furthermore, there is a mounting demand for mandatory transparency that forces a full cost accounting of AI's energy and water footprints before procurement. The future energy system must be built with green code baked into the architecture, both physical and digital.
The ultimate takeaway here is one of necessity. The global data center electricity demand is projected to soar from 460 terawatt-hours in 2022 to an estimated 1,050 terawatt-hours by 2026. This requires not just clean power, but firm clean power that can deliver capacity factors in the 90% range. This scale of energy demand is what makes these high-density, high-capacity factor hot core solutions so critical.
And that leads to our final provocative thought for you to consider. While our dedicated research team notes that current near-term climate goals still depend heavily on technologies already available, wind, solar, and storage, the true role of hot core technologies like fusion and advanced geothermal is not to solve the next 3 years, but to define the grid for the next 50.
It forces a fundamental question about the future of energy production. As the capacity factors for high-density power, which are often in the 85% to 95% reliability range, begin to rival the density and continuous availability of fossil fuels, what fundamental trade-off will we prioritize as an energy system?
Will the future of clean energy be defined by maximizing land use for low-density, intermittent sources, or by prioritizing high-density thermal cores that require far less land and deliver reliable, continuous power to the burgeoning and massive demands of the digital economy? This is the fundamental trade-off we're facing for Tomorrow Unveiled.
Thank you for joining us.
We'll see you next time on Tomorrow Unveiled.